All right, today we're going to crack the code on a totally invisible world. That is, well, all around us. There's this one single, super elegant law that explains everything. I mean everything. From how a car's airbag inflates in an instant to why your soda can fizzes when you open it. We are talking, of course, about the ideal gas law.
You know, it's actually kind of wild to think about, but we're literally living at the bottom of an ocean of gas. We see what it does everywhere, right? Think about the sheer force that lifts a hot air balloon up into the sky, or just the simple pressure that keeps your bike tire firm. It all comes down to this. Heated gases expand, and that one simple fact, it has some seriously powerful consequences.
And that's the real mystery here, isn't it? How on earth could scientists find these predictable mathematical patterns in something they couldn't even see? Well, they basically treated it like a crime scene. They were hunting for clues. So let's dive in and see how they cracked this incredible case.
Okay, so to solve any mystery, you first have to identify the key players, right? These are the four fundamental properties that describe any gas. So let's go ahead and line up the usual suspects.
First up, we've got pressure. We'll call it P. Now, this is just that constant push that gas particles are making as they slam into the walls of whatever container they're in. It's literally the force you feel when the wind blows right in your face.
All right, next on the list is volume, or V. Super simple, it's just the amount of space the gas occupies. And here's the key thing to remember about gases. They will always expand to fill whatever container you put them in. So the volume of the gas is really just the volume of the container. Our third suspect is the amount of gas, which we'll label with an N. Now, in chemistry, we use this unit called a mole to measure it. Don't let that word scare you. Just think of it like a dozen. You know a dozen always means 12, right? Well, a mole is just a specific, really big number of particles. It's just a convenient way for us to count gas particles without dealing with insane numbers.
And last but not least, we've got temperature, or T. And this is where things get really interesting. See, for a gas, temperature isn't just about hot or cold. It's a direct measurement of how much energy those little particles have, how fast they're zipping around. The hotter the gas, the faster they move. And one crucial thing here, for all these calculations, we always use the Kelvin scale. Why? Because it's an absolute scale. It starts at absolute zero and has no negative numbers, which, believe me, is super important for making the math work out.
All right, so now that we have our suspects all lined up, early scientists started doing some detective work. They began to notice patterns by isolating them, you know? They'd look at how just two variables were connected while keeping the other two locked down. And these were the first crucial clues.
So let's look at the evidence file here. You've got Robert Boyle, who figured out that if you squeeze a gas, increase the pressure, its volume gets smaller. Makes total sense, right? Then Jacques Charles comes along and sees that if you heat a gas up, it expands. Its volume increases. Just picture a hot air balloon. And finally, you have Amonten's law, which showed that if you heat a gas in a rigid container, one that can't expand, well, the pressure just builds and builds. Each one of these laws was another critical piece of the puzzle. Now, these separate laws were awesome clues for sure, but the real breakthrough, the big aha moment, came when scientists realized they weren't actually separate rules at all. Nope. They were all just different sides of one single, incredibly powerful idea.
Think of it this way. Each of those simple laws was like a different shadow being cast by the very same object. Boyle's law, Charles's law, Amonten's law, they were all just giving us different angles on a single unified relationship between our four suspects: pressure, volume, amount, and temperature.
And here it is. This is the solution to the entire mystery. PV equals nRT, the ideal gas law. This one beautiful, simple equation combines all of those earlier clues into a single master key that just unlocks the behavior of gases.
So let's break down this master key real quick. On one side, you have pressure times volume, and that's equal to the amount of gas, N, times the temperature, T, times R. So what's R? That's called the ideal gas constant. You can think of it as a kind of universal translator. It's the one number that makes sure all the different units for pressure, volume, and temperature can all speak the same mathematical language. It's the gear that connects the whole machine. And the best part? With this equation, if you know any three of those variables, you can always figure out the fourth.
Okay, but why does this equation work so darn well? I mean, what's really going on underneath it all? Well, to get that, we need to look at the model that scientists came up with to explain how a perfect or ideal gas would behave.
So, this whole law is built on a really powerful idea called the kinetic molecular theory. And to make things work, it makes a few key assumptions. Think of them as the ground rules for our ideal gas. Rule 1, gas particles are just tiny, tiny dots that take up basically no space themselves. Rule 2, they're always moving in constant, random, straight lines until they smack into something. Rule 3, every time they collide, it's perfectly elastic. No energy is ever lost. Imagine them as super bouncy billiard balls that never slow down. And finally, Rule 4, the particles completely ignore each other. No attraction, no repulsion, nothing. By setting up these simple rules, we get a simplified ideal gas that's way easier to describe with math.
Now, don't get me wrong, that model is incredibly powerful. It describes how gases behave with amazing accuracy, most of the time. But here's the catch. It's describing a hypothetical perfect gas. So, what happens when we push real gases to the extreme and they stop playing by those ideal rules?
So what happens when you really push the limits? Well, if you crank up the pressure super high, the molecules get squished so close together that their own tiny size suddenly starts to matter. Or if you drop the temperature way, way down, they slow down so much that the tiny little attractions they have for each other, well, you can't ignore them anymore. And this is where our perfect, ideal model starts to show some cracks.
This really gets to the heart of it. An ideal gas is our simplified hero. The particles are just points in space, and they totally ignore each other. It works great when things are calm, at high temperatures and low pressures. But a real gas is a little more complicated. Those molecules have a tiny but real volume, and they do feel weak attractions to each other, especially when it gets cold and crowded. Now, under normal, everyday conditions, these differences are so small you'd never notice. But when you get to those extreme pressures and temperatures, oh yeah, they definitely start to matter. And of course, to account for this messier reality, scientists came up with an upgraded equation. It's called the van der Waals equation. Now don't worry, you do not need to memorize this thing, but just look at it for a second. See how it's basically our friend the ideal gas law, but with a couple of extra bits tacked on? Those are just little correction terms. One that accounts for the volume of the molecules themselves, and another one that accounts for the attraction between them.
So, does that mean the ideal gas law is wrong? Absolutely not. It's an incredibly powerful tool, a brilliant model that works perfectly for what it was designed for. And it shows us something really cool about how science works, right? You often start with a simple, elegant model to get your head around the basics, and then you build on it, piece by piece, to explore all the fascinating, complex details of the real world. And that journey, that constant process of refining our understanding, well, that's what science is all about.